The number of moose in Massachusetts is growing at the rate of f of x equals 10 e to the 0.03x, where f of x is measured in moose per year and x is measured in years since the year 2000. Let f of x be the moose population in Massachusetts as a function of years since the year 2000. Suppose f of 0 is 300. Find a formula for f of x. Okay, we know that f of x is equal to the initial population plus the change in population. And we know that the initial population is 300, and we can represent the change in population with this. We know it's the integral of the rate of change itself, 10 e to the 0.03x dx, going between 0 and some moment in time x. Okay, so now I see actually, maybe I shouldn't use x over there because I don't want to have the same x here. So how about we make both of these things t's? It's just a notation thing, but you don't want to use the same variable inside your integral as is on the integral itself as one of the limits. Okay, and so that's, this piece of it is just one of our fundamental theorems, right? That I guess it's not so much, well, yeah, I guess it is the fundamental theorem, is that the integral of a rate of change is the actual change in the thing itself. So this piece is the actual change in population. Okay, so what remains is to actually do that integral. So let's do it, 300 plus. Okay, we're interested in an antiderivative here. This feels like a u substitution to me. We're going to let u equal the power 0.03t. And then we'll take a derivative, 0.03 dt, and then we'll solve for dt. So it's du over 0.03. And let's go ahead and then go back to our integral now. The 10 inside is a constant multiplier. I'll put it outside. E to the 0.03 t. So that's really e to the u. And then instead of dt, we're putting du over 0.03. And then instead of going 0 to x, I really do need to change that right now because 0 and x are values of t, and we're supposed to be putting in here values of u. So if t equals x, then u equals something, and if t equals 0, then u equals something. So the thing we're plugging into is right here. U is always 0.03 times t. So 0.03 times x, and 0.03 times 0 is just 0. So those are the two new limits of integration, 0 and 0.03x. Okay, let's wrap this up here. 300 plus. 0.03 is a, well, 1 over 0.03 is a constant multiplier. I'll put it outside, but make sure you keep it on the bottom. The integral of e to the u du is just e to the u. And then we're evaluating this thing between u equals 0 and u equals 0.03x. We don't need to go back to the t's. We've already done the substitution here in orange. So 300 plus. I'm just going to approximate here 10 divided by 0.03. I think it's 333 and change. Let's make sure. Okay. So roughly 333. And then we're going to plug in to e to the u. So e to the 0.03x minus e to the 0. And that answer is okay, but let's simplify just one final step because e to the 0 is 1. And so that really multiplies out and gives you a negative 333, which we can combine with the 300. So I think I get negative 33 and change right there when I smush those together. Negative 33 and a few more 3's plus 333 e to the 0.03x. So that right there is a formula to find the moose population at any moment in time x.